We're going to talk about inference workloads and different challenges of deploying models to production. So we start with a quick introduction. We'll talk about basic requirements for a model serving system and how a model serving system is different, has different requirements from a classic web serving system. And hopefully we'll even have time for a quick demo. So as for the introduction, if we just talk about the three different main stages of the machine learning lifecycle, we have the first stage where we kind of prepare the data, we clean it, we label it, we then prepare a data set, right? Moving into the model training phase where we take the data set, we then explore models, we run model training at scale with hyperparameter optimization, things like that. And then once our model is deployed, we are ready to move it to production, where it would then be able to serve requests from users and provide real value and insights. So we're going to talk about the last stage here of running inference in production. Now, it's important to understand that machine learning is different. It's a completely different ballgame from traditional software engineering, right? And just deploying web applications to production is different, does not have the same requirements as deploying a model serving system, right? We're talking about with machine learning, it involves a lot of experimentation, research activities. So there are some key differentiators. We're going to talk about them. So I'm going to talk about three basic requirements. There are other requirements as well, but we're going to talk about these three. And we'll see how web serving is different from a model serving system. So starting with latency, refers to the time taken to process one request. So imagine we have some web server that is hosting our machine learning model, and we have requests coming in, and the latency measures the time that is taken to process one request. And usually with machine learning and with models running in production, we'll have some latency requirements that will be defined by the application SLA. So let's say we have a requirement that a request must be answered within, let's say, 200 milliseconds, right? So this is one requirement, that we will have low latency, as low as possible. Another requirement is high throughput. So throughput refers to the rate of incoming requests and how they can be processed by a single server. So again, if you imagine that we have a web server hosting our machine learning model, and it's running on compute resources, right, on hardware resources with an associated cost. So the throughput measures the rate of incoming requests that can be processed by a single server. And this translates directly into the deployment cost, if you think about it, because if we have higher throughput, it means that we can serve more requests on the same hardware resources. Okay. Now, both low latency and high throughput are requirements that are not unique for machine learning serving. There are also requirements for basic web serving system. However, the next one, maximizing GPU utilization, is unique to machine learning and to model serving system. So as some of you might know, then GPUs are high and very commonly used with model training, right? Because GPUs are very good fit to and can take a very large data set and then kind of iterate through it very quickly. So that's why it's very typical to use GPUs for model training, as these are very long, compute intensive kind of workloads. However, GPUs can also be highly beneficial for inference workloads, and just for the things that we just talked about, like getting lower latency or getting higher throughput, GPUs can be extremely useful for that. The thing is that with inference workloads, as opposed to training, as we don't need the backpropagation process like we did in training, then the actual computation done on each processing step is much lower than in training, as well as the memory footprint is much lower. And that's why we see with many companies that we work with that when they're running inference workloads on GPUs, the GPU utilization is very low. And we talk about somewhere between 20 to even 15 or 10% utilization of the GPUs. And this is a real shame. And if you think about it, it also translates to a very high cost because these GPUs are very expensive. And you know, just thinking about this, if only 20% or 10% is being utilized, 80 or 90% of this very expensive GPU is actually going to waste. So that's a big problem. It can be a very significant problem. Now, when we're thinking about how we should integrate machine learning into production, you can think about the most naive and simple approach would be taking the same web server that you're using to host your application that handles the business logic, and you can think, okay, I can embed my machine learning code, my model into this kind of server. But because the requirements are very different, right? Like the web application that handles the business logic will not need GPUs, right? It will be probably network bounded and work on commodity CPUs. My model will need GPUs. There will also cause problems with, you know, who's in charge, right? If there's some issue in production, who do you go to? Do you go to the machine learning engineer? You go to the software engineer? And so this is a problem. And what we believe in, and we see in the industry, that the better approach is to kind of decouple the business logic application server from the model serving system. So we need to have like a dedicated model serving system, as you know, it has different requirements. And as was discussed in earlier talks today, Kubernetes is kind of the new standard for container orchestration. Data scientists like to use containers. They want to use Kubernetes. What we did in Run AI is we built a model serving system on top of Kubernetes. Okay, so for those of you who are familiar with Kubernetes, it was not designed for deploying, inference workloads or training, deep learning models. And it was designed for deploying microservices, right? For the classic world of software engineering. And the basic scheduler the default scheduler that comes with Kubernetes does not have a lot of the capabilities that are needed for a model serving system. So what we did in Run AI is we built our own scheduler that is dedicated and specifically designed for deep learning, for AI, for different types of workloads, both for training, for building models, but also for model serving. So our scheduler can manage multiple queues and have priorities between the queues, and this will help us satisfy the SLAs that we discussed earlier. And it also can bring a unique and different auto-scaling policy to each service, and this can help us with auto-scaling based on GPU metrics as well as load-based metrics. Now, for the demo that I want to show you today, we're going to see a very useful capability of Run AI, which is running multiple containers on the same GPU. If you remember, one of the main challenges that we talked about earlier was the fact that even though GPUs can be extremely useful for running inference workloads, as they can help us get lower latency and much higher throughput, the utilization of the GPUs would be very low when running inference workloads, because these inference workloads will only utilize like 10%. They won't need more than that. The GPU is a very powerful thing. So what we did in Run AI is we built and we embedded this capability into our scheduler. We built this technology that allows you to run multiple containers on the same GPU. And this can run on any type of GPU, okay? Even like older GPUs, consumer GPUs, any GPU that had CUDA support, this can work on. And you can fraction the GPU to any number of slices. And the beauty is that it does not require any hypervisor, any code changes, any configuration changes, any image changes, and nothing at all. So let's see how this works. I tell you we can have time for a quick demo. So what you can see on the screen now is I created a Kubernetes cluster that has CM master nodes. I have 2 GPU servers and 1 CPU node. And you can see on the table here that each of my GPU nodes has 2 GPUs each, right? Now, what I prepared is 2 Kubernetes deployments. We can see the YAML files now. Just load them up here. So these are, standard Kubernetes deployment YAML files that you can see on the screen now, right? You can see the deployment. I'm going to run them on this namespace. This is the name that I gave this deployment, Inference Server Demo. And it's going to use Marian server, pretty standard inference server. So I'm going to use this image here. And I'm going to first run a deployment. So deploy this inference server on 1 GPU, okay? And I'm also going to create a service to then be able to communicate and work with this server on port 8888. Now notice that under the spec here, I'm going to use the run AI scheduler instead of the default scheduler. Now, when just running and deploying on a single GPU, this is something that it is available by the default scheduler. Of course, with run AI, you can also give priorities to different applications and users. But let's see how we kind of go and deploy this model. So I can go back to my terminal and I can run the kubectl apply command and deploy this YAML file that we just saw together. And then on the bottom section of the screen, I'm looking at all of the pods that will run inside my run AI tmA namespace, and we see that this new inference server pod is now running. Okay, you see that it was scheduled on the first GPU node, GPU 0 node. And what I can see is if I go and take this pod name, I can look at the logs of this pod name, and I should see the server running. Okay. So I see that indeed the server is listening on port 8888. Everything looks good. Next thing I can do is I can go and exec into the container running this pod. And I want to see the GPU running inside. So I'll just grab the pod name here. And I'll run the kubectl exec-it to get into the container. And you'll see that once I'm inside the container, if I run the NVIDIA SMI command, I will see that this container is scheduled on a single Tesla K80 GPU, right? It's pretty old, weak GPU. And it has all of the GPU memory assigned to it, right? Because I allocated the whole GPU to this inference server deployment. However, you see that if I go back to my Visual Studio Code, we'll look at another deployment YAML that I created here. And what you see now is, and by the way, you saw that the utilization, I didn't really serve any requests yet, right? But the allocating the whole GPU to an inference server, like we discussed earlier, is kind of a waste because the GPU will be very underutilized. However, what I can do with run AI is I can now deploy another inference server. And this time I'm going to ask for only 0.2 GPUs. Okay. Again, this can only be available because I'm using the run AI scheduler. And I'm going to run 4 replicas of this server. So I'm going to actually run 4 pods, 4 instances of this inference server. And each of them will allocate only 0.2 out of the GPU. So let's go back and deploy this server as well. And what you see now is that if we look at the bottom section of the screen, you'll see that 4 additional pods are being created. You see that all of these 4 pods are created on the same GPU node, right? So we had 2 GPUs on each node. 1 GPU was already allocated by the first server, and we ran 4 additional inference servers on a single GPU. And just like we saw before, if I want to see the logs of the inference server on each of these pods, I can see that it's just like before. I should see it running, right? So even though it's running, only on a fraction of a GPU, the server is running. I can see that it's listening to the right port, and I can also exec into one of these new pods, just like we did before with the first pod. And if you remember, if before we saw that when we run the NVIDIA SMI command, we saw that it ran on a single K80 and it had all of the GPU memory as allocated to it. Now we see that this single pod is also running on a single Tesla K80 GPU, but it has only 20% of the GPU memory allocated to it. So we created this memory isolation where it does not affect other containers running on the node. And with this, you can get much higher GPU utilization. You can run many more inference servers on the same GPU and solve this problem of GPU utilization. And just to kind of summarize it, if we go back to the slides, just to kind of wrap up, I can show you here examples of one of our customers that use this capability of Run AI to run multiple inference servers on a single GPU. You can see different types of GPUs here. So both on a T4, V100, and A100 GPUs. And they got between 2x to 8x throughput increase on their GPUs. So this is something very powerful that a lot of our customers are using specifically for inference. It can also be a good fit for other type of workloads. But with inference, you can clearly see like the increase in the throughput, and you would much better utilize your expensive GPUs. So thank you very much.